to another session in the AWS webinar week. Today we're going to be looking at big data on AWS, looking specifically at running your first big data project, and regardless of whether you've got structured data, unstructured data, semi-structured data, or streaming data, we'll look at how that fits into the overall offerings that we have at AWS in the big data space. Now, one of the first conversations that I have with customers when they start talking around big data projects and processing of that data is along a couple of lines. So the first thing is, well, how large is the data set that you have? And the other facet is, how structured is the data that you want to process and analyze? And so often we kind of look at it on this type of graphic. And so if you look at, say, a traditional database, a traditional relational database is fantastic for relatively small data sets of highly structured data. So most of you will have worked with databases and know that when you load data into a database, you need to know the structure of that data before you load it in so that you can create the schema and the data model for that data to go into. And that works well for relatively small data sets. But as the size of your data grows and potentially the structure of your data becomes a little bit messier, you need to move to something slightly different. So often we'll see NoSQL databases in this kind of position on the graph, where people will put more data into those databases because typically they're much more scalable. And they deal with much less structured data, so you're not quite as bound by that rigid schema that you are with your traditional relational database. Now, we're not going to cover NoSQL today, but it's just interesting to see where it fits into the landscape. And then going further up and to the right, we're then looking at Hadoop technologies, where in terms of the structure, all bets are off really. So Hadoop can really accept any structure of data, be that flat files, or it could be emails, it could be log files, it could be media files, audio, video, etc. It's completely flexible in that regard. And obviously in terms of the size of data that Hadoop supports, it's extremely scalable, so you can push very large amounts of data through it. The fourth technology we'll look at in this particular context is the MPP database. Now, if you're not familiar with MPP, MPP stands for Massively Parallel Processing, and it's a breed of database. It's been around for quite a while, but the market really exploded about 10 years ago, and people really took advantage of the scalability that MPP promised. And basically, we'll look into it a bit later on, but it's a way of still using an SQL relational type of paradigm, but with much larger data sets. So these databases were really designed from the ground up for much larger data sets than the traditional systems. So that's often where we start with customers in terms of what type of data they have and how structured it is. And so the agenda today is we're going to look at it through that kind of prism. So we're going to look at structured data and the MPP databases, and specifically Amazon Redshift. And then we're going to look at more unstructured data type of options, where you're looking at Hadoop, and again specifically the Amazon EMR service there. And then we'll look at streaming data as well. And here we're looking at real-time analysis, and we'll take a look at the Amazon Kinesis service that fits into that space. So delving into MPP databases a little bit. So as I said, this paradigm's been around for a while, but really caught on about 10 years ago, and has now become a real staple of the big data marketplace. And the basic idea behind MPP, as the name suggests, that it's massively parallel processing, and the idea is that you see the compute nodes that we have down the bottom there. That's the layer that within that database you can scale out. So the leader node sits out the front and basically talks to the clients, talks to the rest of the network, but then orchestrates the compute nodes to run in parallel to answer every query that comes in. Now, the fantastic thing about the way that the MPP databases are designed is that each of those compute nodes is a self-contained unit. It's a shared nothing architecture. So each node has got its own disk, its own memory, and its own CPU. And what that means is that at query time, it's not trying to compete with other nodes for resource. And that's why you can scale them out to very large numbers, hundreds of nodes potentially, and still get the return in terms of performance. So you should get a linear scaling effect as you scale it out, simply because they're not contending for resources. You add more nodes. So some of the facets of the MPP databases that have made them very popular is that it's standard SQL. So anybody who has used any kind of standard relational database will feel quite at home with an MPP database because it is ANSI standard SQL. As I said, these databases are optimized for fast analysis. They're not good at transactional type of workloads, so you wouldn't use one, for example, for any kind of application that was running transactions. It's really for those types of analytical workloads where you're asking questions of the data that these things really shine. And as I've said, they're very scalable, so you can start small and kind of scale them out quite widely. So moving on to the specific Amazon service that we have in this space, we've called that Amazon Redshift. The first question obviously is what is it? So as I've said, it's one of the MPP databases, so it inherits all the facets that we've been talking about in terms of scalability, and runs ANSI standard SQL, optimized for analytics, very scalable, so you can start with a very small amount of data if you wish. So the smallest node you can have with Redshift is 160 gigabytes, but then you can scale that as you grow through terabytes into 2 petabytes if you need to. So plenty of headroom there to scale with your data as you grow it. It's fully relational. So one of the things that sometimes people get confused about around the MPP databases is that because of this shared nothing architecture, that affects the fact that it's a relational database, when in fact, even though there's some interesting stuff happening in that compute layer, in terms of the way that you query the database and the way that you act with the database, it's still a fully relational database. And Redshift is also fully managed. So what that means is that we will manage the infrastructure underneath the Redshift cluster for you. So you simply tell us how many nodes you want, and we will then take care of provisioning the infrastructure underneath, installing the software, and presenting you with the cluster that you can then use to then create your tables, load your data in, and run your queries, etc. How does it work? So we've looked at the kind of the basic MPP architecture, and the way it works in terms of data is if you look at a very simple table here, the idea is that when you load the data in, you actually spread that across all of the available nodes in the system. And so a table like this, for example, might sit like this across the nodes. And there are various ways that you do that, which is beyond the scope of this session, but there's plenty of information on the Amazon website and plenty of videos where we go into how you do that. But the idea is that you spread those rows across the disk, and then at query time, the SQL query comes in from the client. The leader node then pushes that SQL query down into the compute nodes, and then every node runs the same SQL, but just against its slice of the table, gets the intermediate result sets back. The nodes may communicate with each other if they need to exchange rows for joins, etc. But again, that's all done at that parallel layer, and then the result sets go back to the leader node, and then back to the client. Now, the important thing, as I said before, is that this kind of parallel architecture isn't exposed to the SQL user. So they don't need to know that you're using an MPP database. They don't need to know how you've distributed the data. They simply see a relational structure as they would normally. They run the query, and the only clue to them that they're running on an MPP database should be that the answer comes back a lot faster. Now, there's a couple of other things that Redshift does underneath the covers to speed up your query performance, and one of them is that it uses columnar storage. Now, a lot of the MPP databases are columnar, not all of them, but typically MPP and columnar go together. And the reason is that columnar storage lends itself really well to the types of analytical queries that customers are running on MPP databases. And all this really means is that if you look at a typical table here, we've got a table with 4 columns. In a row-based system, the database will store those rows on disk as your brain imagines that it would. So basically it'll just write out the entire row, then it'll write the next row, the next row, the next row. Now that works really well for transactional workloads because you can follow an index to the front of that row and then basically do whatever you need to do to that row, read it, delete it, update it, or whatever. However, when you're asking questions of your data, you typically don't want to look at every column in your table. You only want to look at a few columns, but you want to look at possibly quite a lot of rows when you do that, because you're looking for aggregations, averages, functions, analysis essentially. And so with a row-based system, you're going to be doing a lot of unnecessary I/O on the disk because you're going to be looking at columns that you don't really care about. So for example, in this situation, if you were saying, give me the average amount by state, you still got to read over the ID and the age column, even though you're actually not interested in them in terms of the query. Now, if you store the data by column, what that means is that on disk, we basically write out all of the column values together, then the next column, then the next column. And so then when you ask your question that says, give me average age as average amount by state, we can just pick the columns that we need, and we can just run through the disk, pull out all the values we need, and then give that answer back to the client. So again, this is something that you don't need to understand from a query perspective. You don't even need to model for it differently when you create your schema. It's just the way that the database stores the data on disk to try and minimize I/O and therefore get your data back to you much more quickly. Another thing we do underneath the covers is data compression. And the way this works is that when you load data into a table for the first time, we'll analyze the data that you've loaded in and work out what's the best compression algorithm for the data that you have and the data type that you have. And the idea with this is to try and squeeze as much of your data as we can into each block on the disk. And so this is all about, again, query performance. It's not really, the driver for this is not to save disk space, although that is a nice side effect. It's really more about driving better performance because, again, try and reduce the I/O that you're doing on the disk. And again, designed to be something that doesn't get exposed to a user, it simply just happens underneath the covers. One of the other facets of the way that Redshift works, and again, not to go on about it, but it is about reducing the I/O on the disk, is that we have a concept of a zone map. Now, a zone map is something that we create internally for every table and every column. It's not something that you need to manage or create yourself. And the idea is that if you look at a block of data on disk, so if you look on the right-hand side there, we've got those blue rectangular blocks of data. So if you imagine that that's your column information, so we've got values there, 10, 13, 14, etc. And what the zone map is a zone map tracks the minimum and maximum value for each block on the disk. So if you look on the left-hand side there, the zone map for that block basically says minimum value 10, maximum value 324. So what happens at query time is if the user has asked a query that's got a where clause in it that says give me some rows where this column equals 25, then instead of going to the block, we can look at the zone map to say, well, does the value 25 fall between the minimum and maximum for this block? If it does, we'll read the block and pull out the values. If it doesn't, then we can skip that block altogether. And that can give you a dramatic speed up as well, because obviously the less blocks you read, the better off you are. Again, a an automatic feature that's not exposed to users, and so you'll see the theme here with Redshift is that there's a lot of features designed to speed up your queries, but not designed to introduce a lot of complexity into the management or the running of the database. So what's good about Redshift? Well, we've talked a bit about some of the features that drive performance, and we'll look at how that translates for one of our customers. Also, scalability is a big factor for our customers as well, ease of use, and then cost as well. So looking at performance, this was a benchmark done by one of our customers actually, who was using a traditional SQL database. They also were starting to use Hive, so Hive being a SQL layer on top of Hadoop, and they wanted to see how those two technologies stack up against Redshift. So they loaded up 2 billion rows into each of those technologies, and they ran a fairly simple query but quite an intense query, which is basically read those 2 billion rows and do an aggregation for me by month. And what they found there was that ran just over 2 hours in their traditional database, about 35 minutes in Hive, and about 12 seconds in Redshift. Now, this isn't meant to be having a go at the traditional databases, because obviously they're a key part of our landscape, but it's more a comment on the fact that those databases just weren't designed for this type of workload. They're really designed for transactional workloads. As soon as you start to ask intense queries of the data, that's where they start to struggle a little bit. Whereas databases like Redshift have been designed from the ground up for exactly this type of purpose, which is why they obviously deal with these types of queries so much better. In terms of scalability, as I said, the smallest node you can have with Redshift is 160 gigabytes, so that's a great place to start if you just want to start playing around with it. But you can scale that out and you can go all the way up to 2 petabytes if you need to. So the nice thing there is that you can start small, but you know there's headroom. So you know that you can always increase the size of the cluster as your data sizes grow. A key question obviously is how do I integrate with Redshift? And the good news there is that it's all standards based. So from a front end perspective, so a query tool perspective, it's just JDBC and ODBC. And so most of the BI tools should work without any dramas, and we'll then just treat the Redshift database as an ODBC or a JDBC endpoint. In terms of the other side of the fence, getting data in to Redshift, there's a couple of different options. So S3, which if you're not familiar with it, is our object storage service. You can put flat files into S3 and then run a copy command from Redshift, which will pull that in, bulk load that into Redshift. You can pull it straight from DynamoDB as well, which is Amazon's NoSQL database. You can also pull data from Elastic MapReduce, which is our hosted Hadoop service, which we're going to talk about in a sec. But you can also pull it from any kind of Linux box as well, and that might be running on Amazon, or it might even be an on-premise system as well. That's all well and good, and obviously loading up flat files is fantastic when you're running a POC or you're doing some one-off analysis. But what we find is that most customers have got source systems, source databases that they want to move the changes from those systems into Redshift on a regular basis. And so this is where we would introduce some kind of ETL layer. So ETL is extract, transform and load. So you'd extract from the source systems, potentially transform the data and then load it into Redshift. And there's a number of great partners that we have in this space. Informatica obviously being the gorilla in the ETL space, but other players as well, to help you to do that change data capture, to capture those deltas, those changes on the source systems and then load them into Redshift. So what I wanted to do was just to very quickly fire up a cluster for you, just to show you the the ease of use of Redshift. So I'm going to be showing you here this is the console. This is the Amazon Redshift management console, and we're just going to jump over to launch a cluster. We'll give the cluster a name. We'll also give the initial database a name as well, specify a port number, specify an initial user and a password. And then we'll go to the next page, which will ask them some questions about how big do you want your cluster to be. So we're just going to go with, let's say we'll go with a 2-node initially. And there's a couple of different choices there around whether you want more dense storage nodes with lots of disk, or whether you want to go with more of a dense compute type node that's got less disk but more processing power. Here's some questions around whether we want to encrypt the data, etc. We'll just take the defaults there, and then this shows us what we've chosen, how much it's going to cost, and then we can then launch it. And then that will take about 5 minutes to come up. And so I just wanted to show you that quickly, because that ease of provisioning really shows the self-service nature of it, and the power of basically being able to spin up clusters whenever you feel like it. You'll pay for that cluster while it's running, but then once you're finished with it, you can tear it down and stop paying for it. So let's go back to our slides and let's move on to unstructured data. So all the things I've talked about there with Redshift, that's fantastic if you have structured data. It is a database, so you do need to create your tables beforehand like you would normally in a database, and then load your data into that. If your data is coming to you though in a format where you potentially don't know the columns that are in it, or sometimes some columns are there, sometimes they're not, or you want to do some transformation on that data, this is where people start to look to technologies like Hadoop, for example, and specifically Amazon's EMR. So let's have a quick look at what Hadoop is in its most basic form. So we talk about it an Hadoop cluster, and that means that within the cluster you've got a number of nodes, typically commodity machines, on which you've got the Hadoop software installed, and you can then obviously scale that out to larger nodes, larger number of nodes if you need to. So the basic idea, and obviously I'm drawing some fairly broad brushstrokes here, but basically you have an input file and you have your functions, and the functions contain whatever the processing or analysis that you want to do on that file. So the file gets split up, and then that gets loaded into the cluster along with your functions, and then Hadoop takes care of making sure that those chunks of data are distributed amongst all of the different nodes. There's usually a replication factor in there as well, so it'll send the same chunk to multiple machines. That's all configurable and all managed by the Hadoop framework. It'll then run those functions for you and then output a result. Now, the things that people like about Hadoop and the reasons that it's become as popular as it has are that it's extremely flexible. So the functions that we're talking about there are typically very rich languages. So you're looking at Java and Python and Ruby and things like that. And so you're kind of outside the realms of SQL. So SQL, while it's fantastic, can be a little bit limiting. With Hadoop, you've really got that flexibility to use much richer languages. As I've said, it's very scalable. So the whole point of the framework is to distribute tasks across a large number of nodes. And so that means that obviously the more nodes that you throw at the cluster, the faster it can get through the processing. Now, the third aspect of Hadoop, which has made it very popular, is that people treat the clusters often in a very transient type of fashion. Now, you can run clusters permanently, and customers do that, but a lot of customers will actually just spin them up when they need them, push their processing and their files through it, and then shut it down when they're done. So looking more specifically at the Amazon service in this area, that's called Amazon Elastic MapReduce. And what is it? It's essentially a managed Hadoop service. So if we go back to our diagram, it's exactly the same. It is Hadoop, but those nodes that we talked about are running on EC2. So EC2, if you're not familiar, is our basic virtual instance. So you can have instances of Linux or Windows. In this case, we'll spin up Linux instances, but we will take care of not only spinning those instances up, but also installing all the software on them, making sure all the nodes are communicating properly, and then basically we will then present you with the cluster, and you can then use it as you need to. So that takes a lot of the pain out of actually managing an Hadoop cluster, which can often be an onerous task to actually get up and running in the first place. How does EMR work? Well, one of the things that we've done a lot of work with EMR on is to tie it very closely to Amazon S3 to really optimize the way that data is written to and from EMR and S3. So S3 is our service, our storage, simple storage service, if you're not familiar with that. Very scalable, extremely durable, great place to use as a landing area for data. So basically the way this works is you put your data into S3. You then choose the Hadoop distribution that you want for your EMR cluster, the number of nodes that you want in the cluster, the type of nodes. So one of the great things about running in the cloud is obviously you've got access to a very large number of different types of machines. So we have different virtual machines that are potentially more compute intense, or they have more memory, or they have more disk, or they have more networking, depending on your application. So you're not locked into a generic type of node type. The other interesting thing too is that you can add some of the Hadoop apps that sit on top of Hadoop very easily. So some of the standard ones, obviously Hive, Pig, HBase, etc. Again, we make that very easy. So that's just a drop down, which I'll show you, and that gets installed on the cluster once you fire it up. You then launch that cluster using either the EMR console or the CLI, or you can do that through the SDK as well. So a number of options there. And then once that cluster is finished, it will actually output the results back to S3, and that then means that because your data is now safely in S3, which offers you 11 nines of durability, you can potentially shut that cluster down if you like. One of the other things you can do though is you can easily resize the cluster. So if you start your processing and realize actually this file is a little bit bigger than we thought, we're going to need a bigger cluster, then you simply add more nodes, and then Hadoop will take care of distribution of the data, and then you can churn through your job a lot more quickly. One of the other nice things that customers like about having the data in S3 is potentially they sometimes like to launch parallel clusters using the same data set that they've used in their main cluster. So this might be because they want to test a different algorithm, or potentially they want to take the results from the first cluster and feed that into a second cluster. And that works really well because obviously you can fire up those clusters independently of one another. Now something we're going to look at in a little bit more detail in a second is the spot market. So the spot market is aimed at EC2 machines, and what we do is any unused capacity that we have in our EC2 fleet we make available for customers to bid on. And this allows you to potentially use an EC2 instance for a lot less than the normal on-demand price, because you basically bid on it on the spot market. The downside of that is that you could potentially lose that instance at any time if the spot price goes above the price that you've bid. But we'll talk about how we've engineered EMR to make sure that you can take advantage of the spot market without actually potentially causing issues in your cluster. But obviously, once your processing is complete, you can terminate it and then stop paying for it, which is obviously fantastic. Being a cloud-based infrastructure, you only pay for it when it's running, and so if it's only running for 3 hours a day, then that's all you pay for. Now we've talked a lot there about using S3 as the place for the input and output for EMR. You don't necessarily have to do it like that. You can store all your data within EMR as well, if you like, on HDFS, the local disk. And some of our customers do this. So they have a particular requirement for a persistent cluster where they want to run this all the time, and they want to keep the data in HDFS. So that's certainly an option as well. So what's good about EMR? Well, some of it we've already covered. Scalability is obviously a great factor. So Hadoop itself is inherently very scalable, but if you're running Hadoop in the cloud, you've then got access, obviously, to a very large number of nodes that you can throw at your problem. So that marriage of cloud and Hadoop is a great one for scaling your application up. Cost is a factor as well, so we're going to have a bit of a look at the spot market in a second, and then also want to show you firing up a cluster to illustrate the ease of use. So we talked a bit about spot instances and using those to try and drive costs down. So let's look at an example of how that might work. So let's say in this scenario we've got a 4-node cluster, and the duration of our job is 14 hours, for example. So the cost of that would be 4 instances times the 14 hours that they're running, and let's say those instances are 50 cents an hour. That's going to cost us $28 to run. Now if we then go to scenario 2, where we keep our original 4 but we add 5 spot instances to that, then the duration of that job is going to come down, obviously, because we've got more processing power in our cluster. But the other nice thing about that is if you look now at the costings, so our 4 instances that are costing us 50 cents an hour, we're now only running them for 7 hours rather than 14 hours. So the cost of them comes down to $14, and then we add to that the 5 instances of spot, and let's say, for example, that we got the spot instances at half the normal on-demand price of 25 cents. That's cost us $8.75 for a total of $22.75. And so what that means is that not only have we cut our processing time in half, but we've also reduced the cost of the cluster as well. Now you might be saying that all sounds a bit too good to be true. Why don't I just throw spot instances at the whole thing and get this incredible cluster, this incredibly massive cluster that costs me hardly anything and zips through my processing? Well, as I said, the only caveat with the spot market is that we could take that instance away from you if you get outbid in the marketplace. But I want to show you how we've engineered EMR to try and deal with that, to try and help you to use spot in a way that's not going to interfere with your processing. So if you look inside an EMR cluster, you've got a couple of different instance groups here. So the first one is your master instance that basically controls the whole show. You've then got your core instances, and they've got HDFS attached. So even if your data is coming from S3, it's going to use HDFS during the processing of your job. But we've introduced a third group called a task instance group. And these guys are pure processing only. They don't have any disk attached to them. And we introduced these guys specifically for taking advantage of spot. Because what this means is that if these 4 instances were originally provisioned via the spot market, then even if we take the instances away, if they're in the middle of processing something, Hadoop will simply give that job to something else within the cluster. So your cluster will keep running. even though you've had some nodes taken away. And so a lot of customers use spot instances a lot for this purpose, where they'll actually use a lot of spot instances for their task group to try and crunch through their job much more quickly, but they don't really mind too much if some of those get taken away, because they know that the cluster is still going to keep going. Now, the Hadoop ecosystem is extremely vibrant, as many of you would know, and practically every day there's a new project, a new open source bit of software, a new vendor, etc. And so the fantastic thing about using Hadoop in any fashion is that you can use these types of technologies to plug into your Hadoop cluster, and this is no different with EMR. So not only can you use them, but we also make it as easy as we can to install them. So as I said, you'll see a drop down for some of the more mature, the more common ones, such as Hive and Pig and HBase, etc. But we also give you the option to install whatever you like on the cluster using what we call a bootstrap action. And this basically means that you just specify, you just tell EMR where to go and get the files for this particular software or project, and it will then pull those out and install them for you as it's bringing up the cluster. So again, just a very easy way to try and install all this stuff on your cluster without you having to go and do it manually. How are customers using it? Well, every vertical has got their own pet use case for Hadoop. It's, as I said, because of its the rich languages you can use with it, because of its flexibility and its scalability, you can really do some incredible things with it. So we see some amazing things in retail with people building recommendation engines. We see a lot of financial institutions using it for risk analysis, for things like that. We see clickstream analysis being done. We see it being used in genome research, etc. It's really extremely flexible and extremely scalable. So what I want to do now is just to jump back into the console for a second. So you can see there's our Redshift cluster ready to go. So that that's all ready if we want to start using it. We're going to jump over to the EMR console here, and I'm going to create our first cluster. Now, I'm not going to show you all the options here, but I just want to, the main point I want to make here is just the ease with which you can get a cluster up and running. So let's call this, let's say we want to do some sentiment analysis, for example. We'll turn logging off. You can tag your clusters so that when it comes to looking at the billing, you can see what they were used for. And here you can see, with the software configuration, you can choose a couple of distributions. So there's an Amazon distribution which is based on the Apache Hadoop project, but you can also choose the commercial MapR version as well if you wish. And then down here you can see where we've got applications to be installed. You can see that we're automatically going to install Hive, Pig, and Hue. Hue being a visual tool that you can use to interact with your cluster. Now you can choose to deinstall these if you wish, but most people have these running, so they'll be installed by default. And then if we look at this drop down, you'll see there's also options for HBase, for Impala, which is SQL on Hadoop, Ganglia for monitoring, and then Hunk as well, which is the Splunk software that sits on top of EMR. So very easy to add those to your cluster. And further down, we'll have a look at the bootstrap actions as well that you can add in. The other thing I wanted to show you here was the hardware configuration. So it's a little bit busy, I know, but if you look down at this section here where we've got the type of nodes, so these are the three types of nodes I was talking about. So the master, the core nodes, and then the task nodes. And with each of these, you'll see this drop down, and you'll see this large list of different instance types, and there's places on the website that will show you exactly what each instance type has got in terms of CPU and memory and networking power. But you can see they're organized into compute versus memory versus storage. So depending on the nature of your processing, sometimes you're going to want a cluster that's quite memory intensive because you're going to be doing a lot of in-memory work. Sometimes you care less about memory and it's more about storage. And so again, running this in the cloud gives you access to more variety of machines than you would have on an on-premise system. So you can add as many core nodes as you want, and then you've got your task nodes down here, which are doing your those ones that are great for spot. And you can see, say we had 2 of those, we might want to put those on spot, and then we can put our bid price in here and work out how much we're prepared to pay for those. The other thing we've just added actually is the option to add an extra task instance groups, in which case you can put a different family of machines. And the reason we did that was because customers potentially wanted to have different spot prices for different machines, so that if they did get outbid with a particular instance type, they might disappear, but they've then still got another group of machines that's maybe got a slightly higher spot price. And you can add quite a number of different groups there to kind of create a tiered effect in terms of spot pricing. The security stuff I won't go through now, but you can see here we've got the bootstrap action. So basically the bootstrap action then allows you to do a couple of things. You can either use it for configuration or you can actually use it to then install other software, and we'll often provide you with bootstrap actions that say you want to install Spark on EMR. We'll say, here's the bootstrap action. You put that in here. That will then go to probably somewhere on S3, pull the files in, and then automatically create it for you. And then basically you can kick that off. And then that'll go off and start running. Now you could have, for example, fed your function at this point, so you can actually point to the function on disk and say run this, or you can just have the cluster running and then just kind of feed it jobs as you need to. So let's so that was unstructured data. Let's finish off with a quick chat about streaming. So streaming is an area that is becoming more and more important to a lot of customers, where the data that they receive is no longer being given to them once a day or even once an hour. It's actually streaming at them from either mobile devices or from websites, from their clickstream data, or potentially from sensors, etc. And they want to be able to capture that, do some analysis, and then potentially put that somewhere else to archive it or to do further analysis on it. Now, when we initially started to look at this, we went to a lot of our customers and we said, what would you use this type of technology for? What are the use cases in here? And what we found is that even though we talked to people from a lot of different industries, they really started to fall into a couple of similar categories. So the first was just log ingest. So a lot of customers said, I generate a lot of logs and I want to keep them, but I just want I want a service that's actually going to manage that for me. And so if you talk to technology companies, it's often about server logs. Financial services, obviously, it's about financial transactions. And so that was one of the first things we wanted to do, was make sure that this service was durable enough so that if customers did put their logs into us, that we would make sure we would capture that durably. The second scenario was one where people said, okay, I'm pushing stuff in there, but I want to start to have a little look at the actual data itself. I want to have a look at some metrics, and so that might be a dashboard about, if say we're talking to IT, it might be about operational type metrics about the way that machines are performing. If we're talking to the ad tech industry, it might be around the yield that they're getting from their ads, conversion of ads, or data metrics in financial markets, etc. So really that kind of real-time analysis on what's happening on my system or in my market right now. Then some customers wanted to go deeper than that, and they wanted to do some kind of more real-time analytics that had a little bit more grunt behind it. So this was looking at things like data that was coming off sensors, trying to look at those and maybe react to it. So potentially if you get a reading from a sensor that's out of a particular range, then I want to actually do something about that. I want to kick off an alarm, etc. And then you can start to get into complex stream processing as well, where you might actually have some kind of recommendation engine, for example, where you're analyzing the data coming in, but then you actually make a decision on that. Maybe you push something back to a user to recommend something to them in terms of a news article that they haven't read or something that you might want them to buy or look at, etc. So the service that we provided for our customers along these lines was Amazon Kinesis. And if you look at what it is, it's basically a fully managed service for the real-time processing of high-volume streaming data. So let's have a bit of a closer look at what that really means in terms of how it works. So say you've got a number of different data sources and you want to capture all the transactions that are happening there. So Kinesis, the first thing we did with Kinesis was we actually built it across 3 availability zones. And what that means is you can think of an availability zone as a separate data center, and we'll actually write each message to 3 separate data centers, so 3 physical separate locations. So you know that those transactions, those messages are highly durable. So you create what we call a stream within Kinesis. You push those data sources into the stream. We will then hold those messages for 24 hours, and that then allows you to then have consuming applications at the other end that will then read those messages and do something with them. So for example, for those people who just wanted to keep an audit trail of their logs, they might have a consumer application sitting on these orange boxes are EC2 virtual machines with a Kinesis application running on them. They would then write that out maybe to S3. So that's just basically keep an audit log of everything that's happened. But also we want to do some metrics as well. So let's have an application that's looking at the stream and pulling out some relevant metrics, and maybe we'll put that into something like Dynamo, which is a NoSQL database, and we'll put a dashboard on top of that so that our internal users or our customers can see what's going on. Then we might have a different one that was doing analysis that might actually be pushing data into Redshift, for example. Or we might even do something interesting like machine learning. So we want to take the messages and we actually want to push it into something like Elastic MapReduce and then start to run some machine learning algorithms across that. Now the key point here is that the idea with Kinesis is that you would have these different applications running, but they don't interfere with one another. So it's not like a message queue where once the message is read you hide it from all the other applications. You actually want it to be seen by all the applications. So we've engineered it so that these, as I said, they don't interfere with one another. So the logging application, for example, might only look into the stream once an hour and pull out an hour's worth of data, whereas the metrics application might be looking every 10 seconds, for example. But they don't interfere with one another because they have different checkpoints within the stream. In terms of putting data into Kinesis, we have this concept of shards within a stream, and so the shards are basically the way that you scale the service up and down. So each shard will give you 1,000 transactions a second, up to a maximum of 1 megasecond, with a 50K payload per transaction. So from that you can kind of work out, depending on your load, how many shards you're going to need to cope with the load, with the traffic. And then, as I said, we keep those messages for 24 hours within the stream. At the other end, you then build those applications to talk to the shards, and we've provided a Kinesis client library just to make it easier for you to build those applications. And currently, you can write the client library in Java or Python. And that takes care of a few things. So it takes care of things like making sure that every shard has got a worker associated with it, so that you never have a shard that's basically being unread, and it will also increase and decrease workers depending on the number of shards that you have in the stream. It also does that checkpointing that I referred to as well, to make sure that you know where you're up to in the stream. What's so good about Kinesis? I mean, there's obviously other ways of doing it. There's other real-time processing engines out there, and basically a lot of it comes down to the similar types of themes that you hear with other Amazon services, and often it's just to do with the fact that it's a managed service. So the administration of it is pretty straightforward. It's very easy to create a stream, which I'll show you in a sec. You do get that real-time performance, so you do get the ability to capture those messages but then deal with them in real time. Extremely high throughput, so you can obviously scale this out as you need to. And then in terms of integration, we've provided a number of pre-built connectors to different services. So obviously our own, such as S3, Redshift, Dynamo, and EMR, but there are others as well. So if you wanted to use Apache Storm, for example, we've got a spout for that. If you want to use Kinesis as the capture mechanism and pass that to Storm for further processing, you can do that. And also Elasticsearch as well. So if you wanted to push messages straight into Elasticsearch, you can do that. Allows you to build those real-time applications. So that client library really designed to help you build those applications without having to get too low level in terms of talking to the API. And low cost too. So if you look at the pricing on Kinesis, you pay per shard, but also per number of million puts. But those numbers are pretty cost effective when you look at what it's doing in terms of the durability and the management of those messages. So let's just have a quick look at the console. Just wanted to show you how easy it was to create your first Kinesis stream. And it really is just straightforward. So basically it just wants to have a name for the stream, and then you just tell it how many shards you want. So if you put in 2 shards, that shows us that we've got basically 4 megasecond that we can read from the stream. You can write to it at 2 megasecond, and those are the number of transactions that you can put into it and read off it. And then that's basically it. And then we create that, and that will then go and create our stream. Now obviously then after that I need to then go and create my my applications that sit at the back end, but we've got a number of examples that can kind of help you to get up and running with that pretty quickly. So just a quick example. I just wanted to just show you that that again, getting started is pretty straightforward, and there's some good Docker around that as well to help you with that very first application. So just to wrap up, there's plenty of information on the big data page at Amazon, at aws.amazon.com. There's case studies. There's a big data blog, which is excellent if you want to follow that. We post all sorts of interesting stuff on there about how a lot of the services work together. So have a look at that. There's also free trial of Redshift running at the moment. So if you spin up a Redshift cluster for the first time, you can have one of those 160 gig nodes for free for 2 months just to have a bit of a play with. So so do check that out. In terms of what we've got coming up tomorrow, so tomorrow obviously being the last day of the webinar week, we've got a couple of interesting sessions. We've got one called Ask an Architect, where you can jump on and basically ask any questions that you want. So you can go to the website, register for that. The other one we've got is questions of the week, so the different questions that people have been asking in the different sessions. We're going to pull those together, pull out the 5 best ones or the most interesting ones, and then spend about 10 minutes answering those. So that's all. If that's of interest, jump onto that as well. Obviously, heaps of other online labs, training, instructor-led classes as well, and then there's the AWS certification too. So you can find that on the /training portion of the website. And finally, thank you very much for attending. We really appreciate you guys taking the time to be with us today and any other webinars that you've attended this week. So thanks very much. Please do complete the survey because it really helps us to make sure that we're giving you guys what you want to hear. So please give us honest feedback about the sessions so that we can improve them for next time. And we hope that you've enjoyed this session, and we look forward to hearing again from you soon. Thanks very much.